Okay, I guess I can't thank people, but I would really like to thank Hugo for organizing this really nice meeting. Okay, so what I'll be talking, I haven't worked too much on large deviations theory recently, but so I'll mostly be talking about old work. But this is something which maybe it's not, hopefully is not already known by all the people here. And I think there are still some interesting questions so, in this kind of area. So this work is done with Anupam and Sanjeev who are here, and also with some work with KG. Okay, so basically the outline of my talk is as follows. I mean, so I'll give some introduction. It's already known, but so I'll just quickly go through this. And basically what we have is like results for, like we look at heat conduction in harmonic systems. So I'll define the model precisely. And so we are looking at heat conduction, and you can ask what is the large deviation function for the total energy transported across a harmonic chain. And so we have actually some exact results for the large deviation function and also the leading correction to the large deviation function. And that's what I'll talk about. I'll outline the method of like how we do this. And I'll give some applications of how we use this results for testing various things. So these are the applications. And then if I have time, I will talk about some more recent work on current fluctuations on ring geometries. Okay, so you can study current fluctuations on open systems which are connected to reservoirs, or you can also study on like closed systems. But maybe I won't get there. Okay, so this is, like I said, it's mostly old work. So there's some recent work on these current fluctuations on ring geometries, and it's still kind of ongoing work. Okay, so this is, I mean, this is something which everyone knows, but I'll quickly say. So if you look at, so just defining large deviation. So if you look at n-step random walk, then any realization is specified by a path where, and the path consists of n steps. Each step is a random number which can be +1 or -1 with probabilities, let's say, p and 1 minus p. So it's a biased random walk. And so the average of each step is 2p minus 1, and this is the standard deviation for each step. So then I look at the sum of these n steps, and that's the position of the walker after n steps. And what the law of large numbers says that if I look at typical fluctuations, then they are Gaussian. And so this is the form of the Gaussian. And this is, of course, good if I'm looking at scales of order root n. And if I am looking at large deviations, which are order n, then the large deviation principle says that the probability distribution has this large deviation form, and this is the large deviation function. Okay, so one other quantity that's useful to define here is the cumulant generating function, which is this x is the random variable, and I just take the characteristic function. So it's just expectation of e to the power lambda x for this distribution. And given the large deviation form, one expects that this cumulant generating function should have this scaling form. And this, of course, generates all moments of the cumulants of the distribution. Okay, so this mu of lambda is what I'll refer to as the cumulant generating function. So it's log of z and divided by n. So that's what I'll call the cumulant generating function. And this mu lambda and the rate function h of x out here, they are related by this some Legendre transform. Okay, so for the biased random walk, this object is easy to compute, so it's trivial to compute this. And then if you use the Legendre transform, you can find that the large deviation function for the random walk is just this object. Okay, so now what I want to talk about is large deviation in heat transport. So I have a system which is described by Newton's equations of motion. So I have particles in this object, and they just follow Newton's equations. And then they are connected to heat reservoirs, which I will model by some stochastic process. Okay. And then I look at some point and I ask how much, so that I can define a rate of flow of energy, and let's call that J of t. So that's the current, energy flowing per unit time, that's J of t. And then I ask what is the total current in some time t, tau. Okay, so that's just the integral of this microscopic current, and that's the total heat that flows in a given amount of time. Okay, so now this is clearly a fluctuating variable because like I said, this stochastic the reservoirs will be modeled with some stochastic dynamics, which I'll write down shortly. But you can see, given the stochastic, so this system is described by a stochastic dynamics. So, I mean, roughly speaking, this Q is like a sum of random numbers. I mean, they are of course correlated random numbers now because this current, there are correlations between the current. So it's roughly like what the random walk was like sum of random numbers, but it's now sum of correlated random numbers. So it has some distribution of P of Q, and what we expect is that at for large time tau, P of Q should have this large deviation form. Okay, and correspondingly, I have this cumulant generating function, mu of lambda, which is defined from the characteristic function for the heat current. Okay, so now typically what one knows is that at large times, this is the dominant behavior, but there's also there can be so there's a subleading correction to the large time form, and quite often we'll find that this thing is also important. Okay, so this g of lambda. Okay, so so HQ is what I call again is the large deviation function. Mu of lambda is the cumulant generating function, and usually they are related by a Legendre transform. Okay, so why are this interesting? So so one of the things is this fluctuation. There is these things called fluctuation theorems, which say that this large deviation functions satisfy some symmetry relations. For example, this h of positive q minus h of minus q is delta beta into q, which is equivalent to saying that the probability of positive. So I look at a point and ask how much. So typically you'll find that heat flows from hot to cold, but once in a while there's also probability of negative heat flowing in the wrong direction, right? So this just says that those things are quite rare, but it makes it precise what is the rate, like probability of positive to negative events is given by this simple form. So these are very general results irrespective of the details of the process, so that's why they're interesting. So an equivalent statement for this fluctuation theorem is for the cumulant generating function, which satisfies this symmetry relation. Okay, so so the other interesting thing is that using these symmetry relations, one can actually derive things like which are valid in the linear response regime, where, for example, the temperature bias is kind of small, and then you have things called Green-Kubo formula and Onsager relations. So you can derive this, just start using these symmetry relations. Okay, so that's why it's kind of nice. So of course, the large deviation functions are interesting because they give the probability of rare events. And from the cumulant generating function, you can compute all cumulants, and they are something which you can measure experimentally. In fact, we have heard some talks where people talked about measurements in some nano devices of like where you can measure various cumulants directly from experiments. And finally, I think it's interesting because these are possible candidates for non-equilibrium free energies. Okay, and I think we again have heard some talks on this. Okay, so what is my system? So the system we look at is basically it's a harmonic chain. So it's described by a Hamiltonian like this. So there's some kinetic energy, and then you can have like on-site springs at all sites, and then there's some nearest neighbor interactions. Okay, so this is just a harmonic model of particles connected by springs. So this is the Hamiltonian, and these are the equations of motion. Okay, so so for particles from 2 to n-1, so the bulk particles just satisfy Newton's equations of motion. Okay, so so I've also written it here, the equations of motion. So so this is just Newton's equations, and the first particle. So there's a force term from the springs, and then there's some extra part which comes because of this reservoir. Okay, so there's a dissipation part and there's a noise part. So so this is just dissipation constant gamma L times velocity of the first particle, And then there's a noise, and the strength of the noise depends on the dissipation and also the temperature of this bath. Okay, so that's the left bath. And the right bath similarly has a different temperature and maybe a different dissipation constant. So the first and last particles are connected to reservoirs at different temperatures, and they are just given by Landauer equations with different noise strengths. Okay, so I can write this equation in a sort of matrix form because these are completely linear equations, right? I mean, so the forces, like you can see here, the equations of motion, they're completely linear. So I can just write it in some matrix form, and that's what I've done here. So you can define a mass matrix, which is a diagonal matrix with all the mass elements, and the force matrix, which in this case is just a tridiagonal matrix. And then there's a dissipation matrix, whose only non-zero element is the first guy, because that's the only guy who's connected to a bath, and similarly a right reservoir. And then there are these two noise terms, which are some vectors with either only the first element is non-zero and the last element is. So I've just rewritten the equations in matrix form. And again, this is the Hamiltonian, it's just a quadratic form. Okay, now, so since this is a linear model, first of all, what do we know about the steady state and things like that? So the first thing you can say is that, okay, so I define this set of variables which includes all the positions and all the velocities. And since it's a linear model, what I expect is that the steady state should just be some a Gaussian distribution, right? It has to be a Gaussian distribution. And which means that if I know all the correlations in the system, then I can actually find, I know everything about steady state. Okay, so in this, for this set of Landauer equations, you can write it's easy to write a Fokker-Planck equations. And so this is the, I guess in the maths literature, it's called the adjoint of the generator. But it's just the Fokker-Planck operator. And so for the steady state, you just solve this equation. And for the simplest model that was studied by this, for example, these people in 1967, is the model where all the masses are equal. Okay, so that model, then you have, starting from this equation, you can write an equation for the correlation matrix. And in the steady state, somehow you can solve this equation. It's quite non-trivial, but you can find the correlation completely exactly, okay? And so if you know the correlation, then of course you know the steady state exactly, okay? So that's one way to solve this problem. A second way of solving is like, okay, so this is, just by solving the Landauer equations by Fourier transforms. Okay, so basically these are some linear equations, and we know that if you want steady state properties, so the simplest way to, so let me just give a simple example. So let's say I have a single particle in some, and it has equation of motion mv dot equals to minus plus noise. Okay, so supposing I have this equation, and this, of course, I can write a Fokker-Planck equation for xvp, and then I can solve this, and I know that the steady state is given by, so it's easy to show that the steady state is some Gaussian with some normalization. Okay, and but if I just so one way would be to solve the steady state equation and get this. But what I could also do is, like, if I wanted to compute things like what is v square second moment, then I could just in the steady state, let's say, then I can just solve this equation by Fourier transforms in time, right? So I just say that x of t is equal to and I plug it into this equation, and what I would get is something like okay, so I take Fourier transform the noise and also the all the variables. And this has a solution that x tilde omega is equal to Okay, and so I'll call this I can some g of omega times. Okay, so once I have this solution, then if I want to compute things like let's say x square average, I just use this solution and take average over noise, and I will get back that x square equals to kbt by k. Okay, so this is the, I mean, if I am just interested in XV, I mean, I can compute all correlations basically, right? Yeah, so I can compute this also, right? Yeah, and this would be 0, right? In this case. Okay, so I can, I mean, so these are just, and once I know these correlators, then of course I know everything about the steady state distribution, because it's I know that the steady state is Gaussian, right? Okay, so so now instead of one particle, I have just n particles, but it's a similar equation, and I can just solve this by Fourier transforms. And the solution now, instead of this this form, will be some inverse of some matrix, which is Green's function of a harmonic chain. Okay, so this Green's function involves the mass matrix, the force matrix, and the dissipation matrices. So I have a solution in terms of the Green's functions, and this noises, which, okay, so the noise out here is delta correlated white Gaussian noise, and I can find their properties in Fourier space, and so that's given. And then, of course, I can just compute any correlator, right? I mean, so it's just straightforward. So it's clear that I'll find my results in terms of this Green's function. And okay, so in particular, what is the, I'm interested, let's say, in the heat current. So what is the heat current? So I should say, I mean, how do I define energy current in this model? So basically, the way to define energy current is like, so I have a Hamiltonian in this system, and I can write it as so it's I can write it as like sum of local energies, where each energy is consists of PL square by 2 plus some local some term like this. And then I would, to define an energy current, I would write a continuity equation. So if I just find what is the rate of change of energy at a particular point, then I'll find that this has the form of a continuity equation, and I can it looks like J L to maybe L minus 1 to L minus J L to L plus 1. Okay. And J would J might look something like, so J L to L plus 1 would be, so I mean, physically this object is simple. It's basically like, if I look at this particle, then this particle is doing some work on it, then that's actually the energy transfer, so right? And work is like velocity times force. So in this harmonic chain, the heat current would just be velocity of the L plus 1 particle into the force on it due to the previous particle, and that is like minus K times XL plus 1 minus XL. Okay, so so something like this would be, so this is precisely, this would be the energy current from site L to L plus 1. Okay, and so this is, of course, is a fluctuating variable, and I can ask for what is its average and so on. And now, because it's a Gaussian process, and these are quadratics, and so it's easy to find expectation of the current and so on in the steady state, right? So, I mean, basically using this solution, you can work out what is the energy current. And so you get some formula like this, which is called a Landauer formula in the physics literature. And, sorry? Okay, so what is this object tau of omega? It's just like, if you send, so you have a harmonic chain, and you try to send like waves from one side, and you look at how much is transmitted, right? So it has the interpretation of a transmission coefficient. And so it's, I mean, in the physics literature, it has been there for electrons. I mean, exactly this sort of a formula, where Landauer-Butiker, or right? Yeah, yes, I think it's. Okay. Yeah, I don't know. So this, I don't know what one should call this. I mean, this formula existed in various forms in various places. So actually, I mean, this problem was studied in 1971 and by Kasher, Lebowitz, and Rubin and Greer, where they were looking at a harmonic chain with random masses, and they wanted to ask how does the average current decay with system size. Okay, and they had actually a formula like exactly this formula, but they didn't think of it in this way. But basically, they had exactly this formula in their paper. Okay, so this gives the steady state current in the system. Okay, and so this Green's function is something which depends on the mass matrix, the force matrix, and you have to take a matrix, invert it, and find some the one nth element, and then do this integral. So it's a formal expression right now, but in principle, if you could do the integral numerically as a function of omega and get an exact answer for the heat current, right? Okay, and quite often you can actually do this analytically, like you can actually do the integral analytically for an ordered chain, and you can get back exactly the same results as obtained using other methods. Okay, so so now what we are interested, of course, is in so that was the average current in the system, but now we want to look at the total current in time tau, right? So if I take average of this, then this would give the steady state current into tau. Okay, but how do we calculate this? Okay, and so we want to calculate this object in the steady state. Okay, so now, so let us define this object, which is, so we find this generating function, but with the constraint that the initial, that the system starts in some particular initial state. So U is all the phase space degrees of freedom of the system, the positions and the velocities. And let's put a constant that we start from a particular initial condition, and we land up at some final initial state for X and V. Okay, so basically we want to compute this, and then of course we can, if we take this restricted generating function, and then integrate over initial conditions chosen from the initial steady state distribution, and then all possible final values of the variables, then that gives us our generating function, right? This is what we are interested in finally. Okay, so again, in this case, just like looking at the steady state, when we are interested in this quantity, one can follow both these two different approaches. Either look at the Fokker-Planck equation or do solution using this Landauer equations. Okay. Okay, so how would you do the method, first method? So in this case, again, so this already I think Hugo talked about and several other people talked about. So, okay, so we're interested in, okay, so again, I want to say that, so this is, I mean, this is the heat current, because this is the force from the left reservoir, and this is the velocity of the first particle, right? So it's just force into velocity. That's the heat going in from the left reservoir into the system. Okay, and then we integrate over time. Okay, so so this is what I called JT. And JT average is something which we already computed, and now we want to compute the distribution of Q. Okay. So now, so we wrote a Fokker-Planck equation for LP, and then you can also write a Fokker-Planck equation for the joint probability of XU and Q. Right, so you can basically write something like, let's say, Okay, so this is the joint probability distribution that the system has, that Q amount of heat has passed and you are at point X and U. Okay, so this is again exactly a slightly modified Fokker-Planck equation, and you can easily write the explicit form. And then what you can do is you can define the so times this P. So, okay. Okay, and this object, from here, you can see that this object would satisfy some equation L lambda into Z. Okay, so this is what is known as the tilted Fokker-Planck operator that also has been discussed earlier. So, okay, and so once we know this, so this equation, then of course you solve this equation for some, with some initial conditions, and then at large times it will have this form. So it will have the form exponential of the, let's say this, so this is the smallest eigenvalue of this operator L lambda, and these are the corresponding left and right eigenvectors. Okay, so at large times you expect that this should dominate the behavior, and so this is what you expect large times, and then this the largest or smallest eigenvalue, the way you, I guess it's the smallest eigenvalue. Okay, so then you can immediately see that this epsilon naught lambda is like mu of lambda, that's the cumulant generating function. And then you can also get the correction form from this, the largest corresponding eigenvector. Okay, so if I, so G of lambda is given by, you take this product and then multiply it by the probability of the initial state, which is this object, and then integrate over du not du. Okay. So this would give the G of lambda also. Okay. So now, in general, this is quite, of course, solving this Fokker-Planck equation is quite difficult. So I'll just tell you the form of this operator L of lambda. So L of lambda looks like this. So, I mean, this first part is just from the deterministic dynamics, and then this part comes from, because it's coupled to the reservoir on the left, and this is the right reservoir. So this part is just what you would have, the usual Fokker-Planck operator, and then this part comes from the tilt. Okay, so this is the tilted part of the generator. Okay. So now, I mean, this in general you can't solve this or even or find the first, the largest eigenvalue and eigenvector is quite complicated. But what we found is that actually using this Fourier transform method, you can find both mu lambda and G lambda exactly. Okay. So, yeah. Yeah. You can, no, I mean, this is no longer Gaussian because of what, I think. So Z is no longer Gaussian because, okay, see, right now, this of course is like a source term in this equation, but I think it's not Gaussian. The once you have this part, okay, so it's no longer Gaussian, right? Yeah. Okay, so okay, now we'll show that you can actually obtain the solution using just Fourier transforms. Okay. Okay, so now we also want to obtain not just the mu of lambda, but also G of lambda. Okay, so you saw in this Fourier transform method, like when you do this, there's no information on the initial state, right? So I mean, there's no, I mean, your system could have started from some initial position and velocity x naught v naught, but the Fourier transform solution has no information about that. Okay, but to construct this g of lambda, it depends actually on the initial conditions. So somehow you need to put in that, and for that, what we found is that you actually have to solve this not to a Fourier transform, but we have to do a finite Fourier series analysis. Okay, so just imagine that we have a signal which goes from time 0 to tau. So it's of course not periodic, but you can still expand it in a. I mean, you can of course still expand it in a Fourier series, right? So so we just do this now in discrete Fourier series. And so for the noise also you can write the Fourier representation. Okay, so then you proceed exactly like before, but and you find a solution, and so solution now looks like this. So this part is already what I had written for the in this case, but now you have some extra part which has information on the initial conditions. Okay, yeah. No, I mean, see, so that's the trick. I mean, even if you have a function like that, you can always do a Fourier series, right? It need not be periodic. I mean, like, it won't match at the, I mean, so this is 0 to tau. I mean, even though it's not periodic, like, you can always take a Fourier series representation. You repeat it. I mean, you just imagine that it's repeated. Right, yeah. So it's discontinuous, but you can always do this. Right, yeah. So, yeah, so I mean, so let's say you write something like that. T. Then if you want this value, then actually you have to take like maybe x minus epsilon, right? Yeah, yeah. So that would give you this point. Yeah, you could do Laplace, but somehow this is what works. I mean, like, we tried also Laplace and all, but this is what was easiest to handle. Okay. Okay, so now you have these two parts, and but I guess he's saying in time you could still take Laplace, right? I mean, but yeah, that. Okay, so okay, so now here the noise strength is proportional to 1 by tau. So so this object is proportional to 1 over root tau, and while these objects are proportional to 1 by tau, right? So what we'll see is that when you use this solution, this first term corresponds to actually contributes to mu of lambda, and these corrections contribute to g of lambda. Okay, so I won't go through all the details, but basically now the point is that the this q, it's a quadratic function of the noise variables eta tilde and all these coordinates u v. So basically now that we know the properties of the noise and everything, you just need to do some Gaussian integrals. Okay, so if you want expectation of e to the power lambda q, you just have to do Gaussian integrals and then we get all these functions. Okay, so yeah, so and then of course the generating function is given by these objects. Okay, so so again I won't give the details. So the finally what we find very interestingly is that this mu of lambda can be expressed completely in terms of the same transmission coefficient that appeared in the average current. Okay, so I'll write the expression for mu of lambda, and the wave functions and this wave functions of corresponding to the largest eigenvalue, they are also given explicitly in terms of this Green's function. Okay, so these expressions are kind of complicated. Okay, so of course we are not proving uniqueness and all, but it's expected to be unique. Right, yeah. So at least for this system, like this linear chain, it should be unique. But even, okay, so like even you can ask even the steady state, is it unique or not? Okay, so I mean one can cook up simple examples where it's non-unique. But so we assume the uniqueness, I mean, I would say. Okay, so I'll just write the expression for the cumulant generating function that we finally get. So it's given by, again, in terms of this transmission function, which is just the transmission of, like, if you send a wave, how much is transmitted, that function. and then you take 1 minus this thing and then log of this. So delta beta is the temperature difference, these are the temperatures, and lambda is the parameter. So so it's a very simple and nice expression, okay. And from this, of course, you can compute various moments. So the first cumulant would just be the current which I already wrote, and the second cumulant is something like this. So you can check that this this Galavati-Cohen symmetry relation is actually satisfied by this object. Okay, so this result was derived in this paper by Anupam, Sanjeev, who are here. And actually, earlier we had done a similar calculation for a quantum system. So their quantum systems are slightly more tricky. I mean, there's like you have to defining things is kind of complicated, but you can still do the calculation if you define things in a particular way. And if you take, so we had done this for quantum harmonic chain, and if you take the classical limit or like high temperature limit, you again recover this exact result. Okay, and g of lambda, we have an exact expression which I won't write because it's very messy, but it's very explicit. Okay, I mean, so yeah. Okay, I'll give some applications where one can check things. Okay, how much time? 3. Yeah. Okay, so I just want to say you can also generalize this to a 3-dimensional system like this, where you actually get something like trace of log of this, and this is some matrix out here. So it's a bit complicated, but we can actually also do this, and we have actually used this formula. Like numerically, you can actually evaluate it and do various things. Okay, so okay, I don't have. I have 2 minutes. Okay, so one other thing I want to mention is that this papers by Hans Fogetby and Alberto, who also reproduced some of our results, and they this symmetry relation actually they could relate it to some property of the tilted generator. Okay, this the Galavati fluctuation symmetry relation. Okay, so now I'll just maybe talk about one application of this formula. So there's this additivity principle which we have heard several times in this conference, which basically tells you that for a diffusive system, if you know the diffusivity and the what is the mobility, then basically you can compute the entire current cumulant generating function. Okay, so there's a very simple formula using this additivity principle. Okay, so for a harmonic system, if you assume it's diffusive, then you know the thermal conductivity and the mobility exactly. Okay, and so therefore, if you use that formula, you have you get an exact expression for the cumulant generating function. So I'll just show you what the expression is. So I won't go into the details of this thing. Okay, so this is the expression that you get for the current cumulant generating function. If you assume that the system is diffusive. Okay, so you just need it to be diffusive. And then you need this kappa of T, which is the thermal conductivity or the diffusivity, and the sigma of T, which is the mobility. Okay. So given these two functions for the system, you know the complete generating function. Okay. So for our system, this thermal conductivity is actually for a harmonic system. You can show exactly that it's independent of temperature. And then using Green-Kubo, you know that sigma is just proportional to temperature square. Okay. So then this one, this K, what is the K? Okay, I think this K is, okay, it's not important. I can't remember what is this K. It's probably just the coupling, yeah, but it's not important right here. This K is the thermal conductivity and sigma is the, yeah, okay. So now, since you know kappa of T and sigma T explicitly, you can do the integrals and you have an explicit formula for the cumulant generating function, okay, just assuming diffusivity. Okay, so now if you take a 3-dimensional harmonic crystal with disorder, then you expect it to be diffusive, okay? And so we did simulations and which show that it's actually a diffusive system. And then we had an exact formula for the large deviation function in terms of that integral of T of omega, right? So we basically decided to compare these two results, and I'll show you how it compares. So Yeah, so basically this verification of this additivity principle conjecture was earlier done on this KMP model by Pablo and Pedro for stochastic dynamics, and here we are looking at a Hamiltonian system and trying to verify the same this law. Okay. Okay, so this is the system, and yeah, so here, I just want to show that this cumulant generating function as a function of lambda evaluated numerically using these two different approaches. One is using the exact formula that we have, which we evaluate numerically, and then what is given by the additivity principle. Okay, and then you see that it matches exactly. Okay, so it's one of the few verifications of the additivity principle in a three-dimensional system in a Hamiltonian dynamics. Okay, so yeah, so I just want to say that there's this paper by Visco in 2006 where he looks at a very simple model, which is a special case of our dynamics. A single particle with no potential and connected to two heat baths, and they looked at again the heat current flowing through it. And in this case, you can show that the tilted Fokker-Planck operator is in fact like the Schrodinger operator for a particle in a harmonic well, and you can compute z of lambda exactly. Okay, so we verified that using our approach, actually you can recover this result exactly. And there are some interesting things about this model. So there's another, Sanjeev studied one model where it's not a free particle, but a particle connected to a spring, again with the same two heat baths. And this model was actually realized experimentally by Liberto's group. And again, using our methods, one could compute exactly the cumulant generating function. And there actually you can also verify, once you have the solution, you can just plug it into the tilted operator equation and verify that it's actually an explicit solution, right? So you have explicit the eigenstate. And there again, I think he compared with the simulation results, and so it's a direct comparison with the experimental paper. Okay, so I'll just summarize. So basically, I wanted to say that these are interesting quantities, and there are few exact calculations on many particle systems, and they numerically also it's kind of difficult. And in our work, what we showed is that for harmonic systems connected to Landauer reservoirs, you can compute this exactly. And so in effect, we have actually exact expressions for the smallest eigenvalue and the corresponding eigenvector of the tilted operator. Okay, so in some cases, like you can explicitly verify, you can take these objects and just plug it into the equation and verify that they actually satisfy the equation. Okay, and I talked about one couple of applications. So thanks.
Thank you. So this kind of transport through an harmonic chain is kind of singular.
What is singular?
The transport of heat by an harmonic chain is very different from the transport of heat by an harmonic chain.
Right. Yeah. So so I put in disorder.
So my question is, when you, do you see a signature of this on the quantity you are computing on this mu of lambda? Or?
Right. Yeah. No. So the harmonic chain is different in the sense. Okay, if you take an ordered chain, like all the masses are equal, then of course it's not diffusive. Okay, so the current, it's ballistic transport, but you can calculate the current, you can calculate cumulants, and everything is fine. Okay, so now your question is, how is it different from systems with anharmonicity and all, right? Yeah. Okay. So so one system which I talked about is a three-dimensional disordered crystal, where it's already diffusive. Even though it's harmonic, but it's diffusive transport. So then it's like a normal conductor, right? So of course, in the details you'll find some differences, but the method, of course, works for everything. So you'll find differences in scaling. Like, for example, if you how do the cumulants scale with system size? So they would be completely different. in a ballistic system versus a system with diffusive behavior and so on. So those are kind of very interesting like differences between anomalous and ballistic and diffusive systems. Yeah.
Do you expect a breakdown of the additivity principle for closed systems?
For closed systems?
The range, when forcing the current to be very large, as for instance in the KMP, the Kivnis-Marchioro Presutti, when you force the current to be very large, you have this traveling wave solution.
Okay.
Breaking down the additivity principle.
Okay, so this I'm not sure, because I mean, can you use the additive principle on a ring geometry? I'm not sure about this. I mean,
no, it breaks down.
It breaks down. Yeah. So I'm not. Yeah. So this I'm not right. Yeah. So even here, I am not sure how one would apply the additivity principle.
The solutions may become time dependent. And
right. Yeah. So yeah, I don't think it should on the ring. It should work. Right. Yeah.
Thanks.
Basically, you have talked about the stationary problem, and what do you have any idea to analyze that, or do you believe that there is some such general framework for the non-stationary problem?
Okay, non-stationary. You're asking like if I look at transient. Yeah. Right, yeah. Okay, I think it should work because still everything is. So I don't know if Sanjay, do you have any?
In principle, the solution is before integrating over.
Yeah, it's right. Yeah. So in principle, it looks like I think it should just go through even because I mean at some point I put in the initial stationary distribution, but if I don't do that, then I have a solution of starting from arbitrary initial conditions. Yeah, that's right. Yeah. So this can also answer questions about non-stationary.
Other questions? If not, let's thank Abhishek again.